Yeah, my name is Ramon Huber, and I did this work as a student at the University of Zurich in the communication system group. And yeah, my work is finished from my side, but there are definitely open topics where things could still be improved. Yeah, so with that, welcome to the presentation of Python-based TinyIPFIX in wireless sensor networks. So Internet of Things devices have become ubiquitous during the past years because of their dropping price points. IoT devices that are organized in a network are referred to as wireless sensor networks. And wireless sensor networks can be used to, for example, measure the environment using temperature, humidity, or light sensors. The different sensors in the network need to send their measurements towards a central place where the data can be processed. There are many applications of wireless sensor networks. For example, a company could run a wireless sensor network to ensure production quality if, for example, the temperature needs to be kept at a certain temperature. Thinking a bit bigger, also a wireless sensor network could be deployed in a smart city where sensors could measure the energy need of each household and company in order to plan the energy production precisely and avoid energy waste. But wireless sensor networks also bring their challenges. For example, two main challenges are the limited programmability of the devices. Implementing advanced functionality often requires tedious implementation with low-level languages. And also these devices are very energy constrained because they often are placed somewhere where there's no power source nearby, and therefore they often are battery powered. So the goal of this work is on the one hand, to cope with the limited programmability. For this, a new generation of devices was used that is more powerful than older generation devices. And on the other hand, the new devices also can be programmed with high-level languages. On the other hand, the goal is to cope with the energy constraints of the devices. For this, we implement an optimal protocol that can be used to send data in a wireless sensor network. Overall, the goal is to facilitate the work with IoT devices. This could, for example, pave the way towards network function virtualization using powerful IoT devices. So on the hardware side, we used ESP32-based microcontrollers. There are many microcontrollers on the market that are based on the ESP32 chip, and we chose two of them. One is the expressive ESP32 DevKit C version 4, and the other one is the Magina Super B. They have relatively much memory and processing power for microcontrollers, and they support a bootloader that can, such that they can be programmed with high-level languages. On the other hand, we use the DigiXP platform. This is used in our work to add low-power wireless connectivity to the ESP32. Concretely, it is IEEE 802.15.4, which is a very widespread standard for low-power wireless connectivity. On the picture, we can see the XB and the ESP32-based Super B, and they are connected using cables such that IEEE 802.15.4 is added to the ESP32. In terms of programming language, we used MicroPython, which is a lightweight version of Python. It is optimized for microcontrollers and very easy to learn. Especially if you already know Python, then it is basically the same. And using MicroPython, functions can be implemented very quickly. IPFIX is a protocol to send information about traffic flow in a network. The special thing about IPFIX is that it knows two types of messages. There are data messages and template messages. Data messages can contain one or multiple values. And the template messages contain the metadata for the data messages. So for example, if a value is a temperature reading or something else. IPFIX is push-based, which means that senders send their data when they are ready, and there is no way for a receiver to request the data from the senders. TinyIPFIX is the protocol that we implemented in the wireless sensor network to send data very energy efficiently. It is an adaptation of IPFIX to wireless sensor networks and also knows the distinction between data and template messages and is also push-based. In a wireless sensor network, the templates rarely change, because you always want to, for example, send temperature and humidity readings, but not suddenly something completely different. So this means that template messages can be sent less often than data messages because they mostly repeat themselves. This cuts down on the overhead and therefore saves energy. Another way on how TinyIPFIX can save energy is that it is push-based. This means that sending devices can go into a sleep mode because they don't need to be able to respond to requests to send data. In TinyIPFIX, there are three kinds of devices. There are TinyIPFIX end devices that measure the environment and send their data towards the collector. They can send their data either directly to the collector or over concentrators. The TinyIPFIX concentrators also measure the environment, but additionally, they can also receive data, and they aggregate multiple messages that they either received or created themselves into one single message. This leads to fewer messages, but bigger ones sent in the network, which saves energy. They also send their data towards the collector. The TinyIPFIX collector collects all data from the network and processes it. The collector is the only device in the network that is unconstrained. If it receives a template, then it checks whether this template is already known. And if it is already known, then it is just discarded, and else it is stored. The collector extracts the data from the data messages using the known templates. Data is distributed by the collector to the applications using a publish-subscribe message broker. The applications can subscribe to a topic of the message broker, and then they receive the specific messages they are interested in from the collector. In the implementation, we first had to flash MicroPython onto the ESP32 microcontrollers. This is because otherwise they wouldn't understand MicroPython. For this, a tool called ESP tool can be used. Then the XPs had to be configured such that they send the messages to the right destination. For this, a software by the manufacturer can be used, which is called XCTU. Then we had to do some coding. The protocol needed to be implemented. For example, we needed to be able to create TinyIPFIX messages, translate them into bytes objects such that they could be sent over the XPs, and then at the receiver side, parse the incoming bytes and create TinyIPFIX messages out of them again. Then some device-related classes had to be implemented. They handled, for example, the sensing of the environment, sending and receiving messages, and also the connection between the ESP32s and the XPs. Lastly, the collector and some sample applications were implemented. We needed to handle the storing of templates, the extraction of data using the stored templates, and also the publishing of data. And then we implemented 2 sample applications for demonstration purposes. One sample application just logged all the messages to the console that it received, and the other sample application stored all the messages it received to a MySQL database. Lastly, we evaluated the system in terms of overhead, transmission reliability, and energy consumption. For this, we created a test network that consisted out of 4 end devices, 2 concentrators, and 1 collector. The overhead of TinyIPFIX was compared to the type length value approach. We set the length field of type length value to 1 byte, because this is also how long a length field is in TinyIPFIX. The type field was set to 2 bytes, and we assumed that an average value is 4.5 bytes long. This could be, for example, a 4-byte sensor value and a 5-byte timestamp for that sensor value. This results in an overhead for a type length value of 40%. In TinyIPFIX, a template message has 21 bytes of overhead. A data message has a variable amount of overhead. It depends on how many data records are sent in a data message. So overall, the overhead of TinyIPFIX depends on the overhead of a data message and how many data messages are sent until a template message is sent again. In the graphic, we plotted the overhead of TinyIPFIX depending on those 2 factors. And we also plotted the overhead of type length value. We can see that the overhead of TinyIPFIX can go much below the overhead of type length value. For example, if 10 data records are sent in a data message and 10 data messages are sent until a template message is sent again, then the overhead of TinyIPFIX is below 25%. We evaluated the transmission reliability of the system. For this, we made multiple measurements that ran for 1 hour each. we always noted how many packages were sent from the sensors and how many were received at the collector. Between the measurements, we varied some parameters. One was the distance between the devices. So, for example, if the end devices are at a distance of 1 meter to the concentrators, or for example, 5 meters. And the other parameter was whether the XPs were using acknowledgements or not. In the graphic, we can see that mostly over 96% of the packages that were being sent were also received. Only the measurement over 5 meters was lower, and we don't really know why that is, but probably it was just a problem with the measurements. The evaluation of the transmission reliability also showed that the implementation of TinyIPFIX was successful and that it can be used in a wireless sensor network. Then we evaluated the energy consumption of the system. For this, we used the power meter to measure the devices in different settings. We measured them in an idle state when they are sending messages, when they are receiving messages, and in the deep sleep state. The deep sleep state is a special state of the ESP32 microcontrollers, where most of the device is powered down and woken up on a timer. We can see that end devices use less energy than the concentrators. This is because the end devices can enter sleep mode, which the concentrators can't, because then they would lose the messages that are sent to them while they are asleep. Additionally, end devices can be in deep sleep mode, which is much more energy preserving, which concentrators also can't enter. All in all, we were expecting to use much less energy. For example, the deep sleep mode, we expected to use less than 1 milliampere, but we were measuring between 20 and 35. So this could mean that the configuration of the devices needs to be improved in future. We were also interested in the energy consumption of the test network, because this is the closest to a real-world scenario that we could get. We again had some parameters changed between measurements. One was the number of data messages sent per hour by the sensors, and the other whether acknowledgements were used or not. We can see that the concentrators already use much energy, even if they are not sending lots of messages. This is because they can't enter the deep sleep mode. The end devices can enter deep sleep mode when they are not sending anything. So for them it matters much more whether they are sending more messages or fewer ones. Also, we can see that the configuration of the devices should be improved. For example, that the end devices should spend more time in the deep sleep mode, and also the deep sleep mode should be more energy preserving. So in future, a time synchronization across devices could be implemented. This would allow the concentrators to enter deep sleep mode as well, because the end devices would know when they can send messages and when the concentrators are asleep. then the configuration of the devices needs to be improved. For example, functionality that is not needed should be powered off in order to save energy. We can conclude that programming with MicroPython allows for a faster value creation than would be possible with a low-level language like C. And we can also conclude that microcontrollers have become powerful enough to support high-level languages. Lastly, TinyIPFIX has been implemented and is highly portable and energy efficient. So thank you for your attention, and I am open for questions.